Let us talk about counting sort algorithm. Counting sort is a linear time algorithm for the cases when our input elements are in a small range. For example, if we have n elements and elements are in range from 0 to k minus 1, then counting sort is going to take big O of n plus k time. It is not a comparison based algorithm. It never compares items with each other. Rather, it counts their occurrences. Counting sort is useful only when k is linear in terms of n. K is n, n by 2 or 2n or 3n. When k becomes n log n or quadratic, it is of no use because we have algorithms, comparison based algorithms that work for any range and take big O of n log n time. Let us understand counting sort with this example. We have an array ARR with the range of elements from 0 to 4. So we have k equal to 5 and we want to sort this array. So our output array is going to be sorted. Now this example, k is 10, so elements are in range from 0 to 9 and we want to sort this array. So we want this as output. Now please pause this video and try to write down a program that takes an array as an argument, takes k as an argument and sorts the array in big O of n plus k time. Let us first talk about a naive implementation to solve this problem. The first thing that we do in this naive implementation is we create a count array of size k. We know that array elements are in range from 0 to k minus 1. So we can have an array of size k to count occurrences of all array elements. We initialize this count array as 0. Now we traverse through the input array and increment the count of every element that we see. So we are using array elements as indexes in this count array and incrementing their counts. So after this first phase of this algorithm, our count array will look like this. 1 appears 3 times, so you have 3 at index 1 in this count array. 0 appears 1 times, so you have 1 at index 0. 2 and 3 are not there in our input array, so we have 0, 0 as the counts of 2 and 3. And 4 appears 2 times, so we have 2 as index 4. Size of this count array is 5 because k is 5, so we have the size of count array is 5. Size of our input array is n, which is 6 here, right? So we create a count array of size 5 and simply increment count of every element that we traverse in the input array. Now once we have built the count array, how do we use this count array to sort the input array? In this simple implementation, we are using this simple idea. We know that 0 appears 1 times, so we run a loop for count 0, how many times 0 appears, and put 0 those many times. Since it appears 1 times, we are going to put it only once. Now we go to the next element and we get count of it. You know 1 appears 3 times, so we run a loop 3 times and put 1 3 times in our original array, right? So we have 1 3 times. We do not care what elements are there, right? We actually have the same elements at this position, but we are going to override the whole array by considering the count array. Now we go to 2. For I equal to 2, our count is 0, so we do not do anything. For I equal to 3, our count is again 0, we do not do anything. But when we come to I equal to 4, our count is 2. So what we do is, we put 4 at the last 2 positions, and that's what we have implemented here. We are running a loop that traverses through every element of count array. This loop runs from 0 to k minus 1. And what it does, so this loop is basically going to run through this count array, right, that we have built. And what it does inside the loop, it runs another loop that runs count I time for an index I in the count array. And that tells you how many times this I appears your input array, right? That's what count array meaning is. So what we are going to do, we are going to put I those many times at the next index in our original array. So our next index is another variable that we have initialized as 0. So first element, the 0 count, if 0 is there, it's going to be put at index 0. Then 1s are going to be put and then 2s are going to put, right? So for I equal to 0, we have 0 count as 1. So in inner loop is going to run once and it's going to put a 0 here, right? And then this inner loop will stop because count 0 is 1. Then outer loop will run for 1. And for 1 at this loop is going to run 3 times, right? And when it runs 3 times, it's going to put 1 3 times in your array at the next index and it's going to increment the index. So that's how this logic works. Now, what is the time complexity of the solution? The first part of this loop, if you see, it runs theta k times. This runs theta n times. Let's now analyze this loop. This loop runs count I times for every I varying from 0 to k minus 1. And what is the sum of all the counts? It's actually n. So the innermost statements are going to run theta n times. But we have an outer loop also. If k is high compared to n, then also this outer loop is going to run theta k times at least. So we can say the overall time complexity of this part is theta n plus k. So overall time complexity of this algorithm is theta k plus theta n plus theta n plus k, which is theta of n plus k. So that's the overall time complexity of this algorithm. The naive implementation that we have written here, it works in theta n plus k time. It's fast, but it cannot be used as a general purpose sorting algorithm. It can only be used when you have an integer array or an array of items which are integral, like short integer or characters. It cannot be used for sorting objects. For example, sorting an array of students by their marks. Because what happens in this solution is, you are going to use array I as an index. So say you use marks as an index. You have an array of students and you do array I dot marks as an index, right? And you do plus plus. You know that marks are going to be from 0 to 100. You create an array of size 101 and you do array I marks plus plus. Now, once you've done this step is going to fail, because what are we going to do in this step? We are going to assign indexes in the array of objects. And we cannot do that, right? It's a student object which we are sorting, right? Array of student objects. And what are we putting here? We are putting index. So we cannot assign simply marks to the student objects. So we need to come up with an approach that can work for general purpose objects, the objects which have multiple fields. Here is a general purpose counting sort implementation. It works really well when you have objects to be sorted also. And these objects are to be sorted according to a certain key. This implementation works for integers as well. For simplicity of implementation, we are showing this implementation only for integers. So the first step of this algorithm is same as the naive implementation. We have a count array. We initialize this count array as 0 and then we increment count of every array element one by one. So after this step, for this input array, our count array is going to be 1, 3, 0, 0, 2. Count of 0 is 1 in our input array. Count of 1 is 3 in our input array. 1 appears 3 times. And 2 and 3 do not appear, so their counts are 0. 4 appears 2 times, so count of 4 is 2 here, right? So this step is same as the naive implementation. After this step, we modify our count array such that count I stores how many elements in our input array are smaller than or equal to I. And this is what we do in this loop here. We run this loop from second element, starting from index 1. So count 0 is going to be remaining as it is because there is nothing before 0, and number of elements which are smaller than or equal to 0 are going to be the same. When we are at index 1, right, we begin this loop on index 1. What are we going to do? We are going to add count 0 with count 1. So count 0 with count 1. 1 and 3, 4. So we get the value 4. And now when we go to the next index, index 1, what are we going to do? We are going to add count 1 and count 2, which is 4. Now when we are at this index, we are going to add count 2 and count 3. So we are going to get 0 plus 4, 4. Now when we are at this index, we are going to add count 4 with count 3. So we are going to get 4 and 2. So we get 6. So these are the values we get count. And now if you take a look at this count array, count I indicates how many elements in our input array are smaller than I or equal to I. For example, count of 3 indicates 3 is 4. How many elements in our input array are smaller than or equal to 3? There are 4 elements, 3 ones and 1 0. Count 1 also is 4. So how many elements in our input array are smaller than or equal to 1? We have 4 elements, 1 0 and 3 ones. Count of 4 means 6. So how many elements we have smaller than or equal to 4? We have all 6 elements. That's why we have the value 6. Now how do we use this count array to get our sorted array in another array output? So we are going to use this ARR and count to build this output array, and this output array is going to contain all the elements in sorted form. And once we have built this output array, at the end we are simply going to copy this output array back to our original array. Now the most critical part of this algorithm is building this output array. I have cleaned up the board now. Let us now build the output array step by step. So we are traversing this input array from n-1 and we are going till 0 in this loop, right? Please note that we could build the output array by traversing from 0 to n-1 also. The reason we are doing from n-1 to 0 reverse way is to make sure that our output is stable. The sorting is stable. Stable means if there are 2 elements with same value, they should appear in the same order in the output as they appear in our input array. So if this last one appears last in your input array, then it should appear last in the output array as well. That's why we are traversing from the right. Let's see how does this work. So we begin from the last index or last element in our input array. We use this value as an index in our count array and we get the count as 4. So we know that there are 4 elements smaller than or equal to 1 in our input array, which means this 1 should go at the 4th position in your output array. And 4th position means index 3. That is why we have subtracted 1 here. So we put this 1 at index 3. After putting 1 at index 3, we reduce its count also. We make it 3. So that when you see next time 1, you do not put at 4th position, you put it at 3rd position. Now we go to the next element 0 and 0's value is 1. It means there is only one element which is smaller than or equal to 0. So we use this 1, subtract 1 from it and we put 0 here. Basically this 1 tells you the position of 0 is first position in your input array. And we reduce this count to 0. Now we go to the next element and we notice that this is 1. We use it as an index. We get the count as 3 now. Which means there are 3 elements smaller than or equal to 1. So we need to put it at 3rd position. And when we are putting it at 3rd position, we need to put it at index 2. So we put this 1 at index 2 and we reduce its count further to 2. Now we go to the next element 4 and we use this 4 as an index and we get the count value as 6. That means there are 6 elements smaller than or equal to this 4, which means we need to put it at the 6th position, which means at index 5. So we put 4 here and we reduce its count to 5. Now we go to the next one. This one is 4. We use this 4 again as an index in this array and we get the count as 5, which means this should go at the 5th position, which means index 4. So we put 4 here and reduce its count to 4. Now we go to the next element, which is 1. We use 1 as an index and we get the count as 2, which means it should go to the 2nd position and we reduce its value to 1 and put it at 2nd position, index 1. And that's how we get our output sorted array. After we have got our output sorted array, we are simply copying this array back to our original array. So our original array becomes 0, 1, 1, 1, 4, 4. And we have got the sorted array. It's a stable sorting algorithm because we are traversing from the right side and it takes care of objects when you want to sort them according to a particular key, because we are never putting indexes as values in our output array. We are putting actual objects in our output array and then copying these actual objects back to our input array. right? We're not putting indexes that we did in the naive solution. Let's now see one more example to get a better idea of this algorithm. Let's see, we have our input array of size 4 with elements as 5, 6, 5, 2, and our range is 0 to 6. So we make a count array of size 7. We put counts of individual elements. So count of 2 is 1, count of 0 and 1s are 0, 0. Count of 5 is 2, 5 appears 2 times, and count of 6 is 1. After building this count array, we build a cumulative count array where we have count I means number of elements which are smaller than or equal to I. So we simply do a cumulative sum. So this element we get 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 2 is 3, 3 plus 1 is 4, right? And after this step, we are going to build the output array. Let us see now how do we build the output array for this example. We have an output array of same size our input array. Now we are going to traverse our input array from last index. We have the element 2. We use this element as an index in our cumulative count array. We get the value 1. It means this 2 is going to be there at first position in our output array. So we put it at first position and we decrement the count of this 2 in our count array from 1 to 0. Now we traverse through the next element and we use it as an index in our count array 5. We get the count as 3. It means this next element 5 should go at the third position. So we put it at the third position and decrement its count from 3 to 2, right? Now we go to the next element 6. We use it as an index in the count array. We get the value 4. It means the 6 should go at the fourth position. So we put it at the fourth position in our output array and we decrement its count to 3. Now we go to the next element in our input array 5 and we use it as an index in our count array. We get the value 2. It means this 5 should go at the second position. So we put it at the second position and decrement its count to 1. And that's how we get our sorted array. Let us now see some important points about counting sort. The first thing is, it's not a comparison-based sorting algorithm. If you take a look at this implementation, we never compare array items like we do in comparison-based sorting algorithm. The next thing is, it takes theta n plus k time. The first part takes theta k time, then theta n time, then theta k, then theta n, and then again theta n. So overall, it's theta n plus k algorithm. The third is, it takes theta n plus k extra space. We need theta k space for count array and we need theta n space for the output array. So it's going to take theta n plus k extra space. It's a stable algorithm because we were traversing our input array. We are traversing our input array from right side to left side. So we always put right elements first at their last positions, right? That's how it's a stable algorithm. It is used as a subroutine in radix sort. Please note that counting sort is useful only when k is really small. If k is linearly proportional to n, like it's n by 2 or n or 2n. But if k is large, like n square or n cube, then counting sort becomes n square algorithm or n cube algorithm. And that's where radix sort is a better algorithm. It works in linear time even if your input range is from 0 to n square or 0 to n cube. We'll talk about radix sort in a separate video. Counting sort is used as a subroutine in the radix sort. Here is an exercise for you. In this implementation, we have considered elements in range from 0 to k minus 1. Now please extend this implementation so that you can handle the elements from a min value to max value, and we know that total items in this from this min value to max value are only k, and this min value can be negative also.